Aloha, and welcome to our third lecture in the Acids and Bases series. In this lecture, we focus on the pH of weak acids and the ice tables which are used to deal with those systems. So let's begin by comparing weak versus strong acids. We dealt with that comparison in our last video, so let's recall some of that. Strong acids, such as hydrochloric acid, fully dissociate in water. So HCl in solution will dissociate into protons in solution and the chloride anions. That's the conjugate base of that. Now this is a strong acid, so you can visualize it over here. All of the protons are separated from the chloride anions. There are no molecules that are still together because they are fully dissociated. Every single one is split apart. If you're asked to find the pH of a strong acid solution, it's pretty simple. For example, find the pH of 0.1 molarity HCl. And the answer is as follows. Hydrochloric acid is a strong acid. It's one of the 6 strong acids. And so the proton concentration is the same as the concentration of hydrochloric acid that you started with. So the proton concentration is also 0.1 molarity. And we can justify that because if you have 0.1 moles of hydrochloric acid per liter, all of them are dissociated into protons and chlorides, so you will have 0.1 moles of protons per liter as well. And so the proton concentration is also 0.1 molarity. So when you have strong acids and you know the concentration of the strong acid, you automatically know the concentration of proton. And therefore you can quickly calculate the pH. The pH is the negative log of the proton concentration, so negative log of 0.1, and that's 1. So that's strong acids. Weak acids are a little more involved. Let's use hydrofluoric acid as an example. Weak acids, in contrast, are partially dissociated. So strong acids, 100% of the molecules dissociate. Weak acids, only a fraction of them do. Sometimes it's 10%, sometimes 20%. It depends on the weak acid. So hydrofluoric acid is a weak acid, so it undergoes partial dissociation as represented by the equilibrium arrow. So you do get protons in solution and fluoride minus as well. And your picture looks something like this. A couple are dissociated, but the majority are undissociated molecules. And about 1 in 12 of them are dissociated. Now this is an equilibrium which is occurring between the molecules and the ions. The undissociated HF molecules are in equilibrium with the dissociated protons and fluoride ions. And any equilibrium can be measured with the equilibrium constant. In other words, what ratio of this system, what's the ratio of product versus reactant? That's what the equilibrium constant tells you. And the equilibrium constant for this chemical equation at 25 degrees is 6.8 times 10 to the minus 4. When you're dealing with weak acids, the equilibrium constants get the subscript A for acid. So it's 6.8 times 10 to the minus 4. And I'll remind you that equilibrium constants, they represent a ratio of product concentrations over reactant concentrations. So when you have equilibrium constants that are much smaller than 1, that means at equilibrium, there's not that many product in there. Most of it is in the form of reactant. So that's how you want to think about these. Pretty small equilibrium constant, so you only got a few products in there. Equilibrium constants for weak acids are found in the appendices in your Gen Chem texts. So let's do a calculation involving hydrofluoric acid. Suppose you're asked to find the pH of a solution formed by mixing 0.1 moles of HF in 1 liter of solution. That would give you 0.1 molarity. This is at 25 Celsius, and the equilibrium constant for HF at that temperature is 6.8 times 10 to the minus 4. So here you're given the equilibrium constant. You don't have to go look for it. You're told what the initial acid concentration is at the beginning, and you're asked to find the pH, which means you need to know what the proton concentration is at equilibrium. Now, when you're told what you have at the beginning, you're told the initial acid concentration, and you're asked for the pH, which is really the equilibrium proton concentration, you should be thinking of organizing your information in an ice table. So maybe you've seen ice tables before. So let's talk about how to do this. First, our picture looks something like this. The 0.1 molarity of hydrofluoric acid that you mix at the beginning, suppose the molecules haven't had enough time yet to dissociate. So as soon as you put it in the solution, there they all are. So that's what you have at the beginning. Now, as it undergoes the dissociation as represented by this chemical equation, it will reach equilibrium where the protons are now separated from the fluoride minuses. And at equilibrium, the concentrations are no longer changing. So to get from the initial situation to the equilibrium situation, it has to undergo a change. Now, the chemical equation is represented right here, and an ice table looks like this. So right underneath the chemicals, we put what the concentrations are at the beginning, the changes that the concentrations undergo, and what the concentrations are at equilibrium. Now, at the very beginning, you're told that the molarity of the HF is 0.1 molarity. And it doesn't say anything about any proton concentration or fluoride concentration, so you assume that they're nothing. It turns out that water does always have a tiny bit of background proton concentration, but it's so small that it can almost always be ignored. And so that's why we have this approximately 0. Okay, it's ignore. You can ignore it. Just ignore the background proton concentration, which is due to the autoionization of water. It turns out that it's about 10 to the negative 7 molarity, and we'll discuss that in the next video, but it's insignificant compared to the proton concentration that acids give you. So that's why we ignore it. So these are your initial concentrations. Now the coefficients are 1, 1, and 1. So if to get to equilibrium, this loses a certain amount of concentration, x and minus x, to get to equilibrium, then these will gain that same amount of concentration, x, and plus x. So the initial concentration plus the change will be the concentrations at equilibrium. So 0.1 minus x is what you'll have at equilibrium for HF. 0 plus x gives you x, and that will be the equilibrium proton concentration, and the equilibrium fluoride concentration will also be x. So here are your equilibrium concentrations for this system, and if we knew what x was, we can then figure out what the pH is. So like any equilibrium, we can write the equilibrium constant expression, or I should say for any equilibrium, we can write the equilibrium constant equation. So here it is, and it's the ratio of product concentrations over reactant concentrations. And all the coefficients are 1s here, and so the concentrations are just raised to the 1 power. It's pretty simple. So here's the equilibrium constant equation. So we plug in the equilibrium constant and the concentrations involving x, and there we have that equation, and we can solve this equation for x. So solving it for x, it's a nasty looking equation, and you'll end up, it's a quadratic equation. So, if you multiply everything out, you can use a quadratic formula or completing the squares or whatever type of technique you like to do for solving this equation. You can just plug it in your calculator and let the calculator do the work for you. That's what I usually do. So solving it for x, you get two answers. Quadratic equations give you two answers. In this case, you get a negative answer and a positive answer. One of them is always the correct one. Okay, you just have to look at the two and see which one doesn't make sense. You can't have negative concentrations. It has to be this one right here. So the proton concentration at equilibrium is 0.007913. Okay, so that's your proton concentration, 0.007913. Now we can estimate the pH now that we know the proton concentration, because this is greater than 0.001 molarity, which would be pH 3, but it's less than 0.01, which would be a pH 2. So our system is going to be pH 2 point something. And when we plug in our proton concentration into the pH equation, negative log of 0.007913, we get the pH as 2.10. And so there you go. You got a pH of 2.10. Now, one other thing, if you remember, we said that about 1 in 12 of the molecules of HF are dissociated. So where do we get that 1 in 12 from? Well, one way to get it is to calculate the percent ionization. The percent ionization is calculated by the equilibrium proton concentration over the initial acid concentration times 100. It's basically the percentage of molecules of the acid that dissociate. That's what it is. So the equilibrium proton concentration we know is 0.0079, and the initial acid concentration is 0.1, so the part over the whole. You calculate this, that comes out to 7.9%. And 7.9% is 1 in 12.7. So if you take 1 divided by 0.079, you get 12.7. So that's where the 12 comes from. So it looks like it's closer to 13 in this case. So about 1 in 13 molecules of HF are dissociated. It's a pretty tricky problem. So weak acids, let's go through it one more time. If you know what the concentration of weak acid is at the beginning, then you're not sure how much dissociates. So we just say that X amount dissociates. You lose X amount of reactant. So this is what you have at equilibrium. It's the initial minus X. In the products, we're not sure how much of them are formed at equilibrium. So, if you lose X amount of reactant, you had to gain X amount of the products here and there. And so at equilibrium, you got X amount of products. Okay, but we know the equilibrium concentrations can be plugged into the equilibrium constant equation. Okay, and if you know what the equilibrium constant is and you have the concentrations involving X, then you can solve for X and figure out what the equilibrium concentrations are that way. So it takes a little bit of work to figure out what your proton concentration is. The ICE table is a great technique, and once you know it, you can then quickly calculate the pH. Let's do one more example of a weak acid. Suppose you're asked to calculate the pH of a formic acid solution that contains 1.5% formic acid by mass. So you're told the mass percent here, and assume the density is 1.01 grams per milliliter. So this is a little tricky problem. You're not told what the initial molarity is, but you're told what the concentration is by mass percent. So you need to convert the mass percent to molarity. and then proceed as we did in the last problem. First, this is formic acid. Here's the Lewis structure for formic acid. It's the proton that's attached to the oxygen atom, which is acidic. So this is the one that comes off, and this is a weak acid, and here's its equilibrium constant at 25 Celsius. Okay, and you're also told that the density is 1.01 grams per milliliter. So if you had a milliliter of solution, it would weigh 1.01 grams. So there you go. That's one little milliliter of solution, and the mass of that solution is 1.01 grams. So our first job is to take the information that it gives us and figure out what the concentration is in molarity. So let's determine the molarity of formic acid. Molarity is moles over liters, N over V. So we need to find the number of moles of formic acid and the number of liters of formic acid. So it doesn't really matter how much solution you consider. So why don't we consider that one little milliliter of solution? The 1 milliliter of solution we know weighs 1.01 grams, and 1.50% of that mass is formic acid, because we're told the mass percent of the solution. So that's how we figure out the mass of formic acid in that milliliter. So 1 milliliter weighs 1.01 grams, that's the density, and it gives us the mass percent. 1.50% of that mass is formic acid. So if we take the mass of the solution and multiply it by 1.5%, that's 0.015, then we get the mass of the formic acid in that milliliter, which is 0.01515 grams of formic acid. So now we know the mass of formic acid and the volume of solution. So we take the mass of formic acid and, using its molar mass, calculate the moles of formic acid. So that's moles of formic acid up there. We need to divide that by the liters of solution. So 1 milliliter, convert that to liters. So this is the liters of solution down there. And when you run this calculation, you get 0.329 molarity. So that's the molarity of solution of formic acid. It took a little bit of work to get that. Now we know the concentration of the acid. We can solve a nice table to get the concentration of protons at equilibrium. So let's write the equilibrium chemical equation. Here's our formic acid, that's the proton right there. And it establishes equilibrium with the formate anion and the proton right there. Now that we know the initial concentration of the formic acid, and it didn't say anything about initial concentrations of anything else, so you had no formate at the beginning, and ignoring autoionization of water, you have no protons at the beginning. So to get to equilibrium, the reactant, formic acid, loses a certain amount of concentration, X amount, and therefore the products gain X amount and X amount. And at equilibrium, you got 0.329 minus X for the formic acid, and X for the formate, and X for the proton. Now, with this equilibrium chemical equation, we can write the corresponding equilibrium constant equation. And we're told what the equilibrium constant is, so we plug that in for Ka. And we also have the equilibrium concentrations right here involving X, so we plug those in. And when we solve this for X, again, we get two answers because it's a quadratic equation, a complicated one to solve. It might take you a little while, but you can solve it. And you'll get two answers, and only one of them makes sense. You can't have negative concentrations. It has to be this one. So that's the proton concentration at equilibrium, 0.0076. So now that we know the equilibrium proton concentration, in the last step we can calculate pH. So your proton concentration is 0.0076. We can estimate the pH quickly. That's greater than 0.001 but less than 0.01. So again, our pH is going to be between 2 and 3. And when we plug this into the pH equation, the negative log of 0.0076, include those extra digits for error, but it's significant right there. You have 2 sig figs, and when you calculate this, you get 2.12. So that is the answer right there. So weak acids are a little more involved. You have to solve an ice table to get the proton concentration, and then you get the pH. Strong acids, you have the proton concentration right away, but weak acids, it takes a little more work to get them. So that's how you do it. And in our next video, we will discuss the auto-ionization of water. So stay tuned for that. Aloha.